In this talk, I will discuss introduction to the magneto-transport theory of Dirac and Weyl semimetals. So this is the outline of this talk. I will introduce what are Dirac and Weyl fermions. Then I will discuss the Berry phase effect and the chiral anomaly effect. Then I will discuss my present work that deals with the semi-classical magneto-transport theory. And then I will discuss Lorentz force and a force that is arising due to the Berry phase effect, that is the Berry force, the Berry phase related force. Then I will discuss quantum magnetotransport in Dirac and Weyl semimetals. So we have discussed, so we will be discussing both the semi-classical magnetotransport and the quantum magnetotransport. Then I will discuss the violation of Lorentz symmetry that is very particular in the particular observation in these semi-metals. So we will discuss the tilt in the energy dispersion that leads to the violation of Lorentz symmetry. And then this tilt leads to the planar Hall effect that we will also discuss. And at the end, we will give conclusion. So why all the interest in Weyl and Dirac semi-metal? So Dirac tried to write Hamiltonian for a spin half particle, and he spin half relativistic particle. So he ended up with this Hamiltonian. And in his mind, spin half particles were electron, which has mass 9.1 cross 10 raised to the power minus 31 kilogram. Now the Dirac ended up with these 4 by 4 matrices, and when he find out its solution, it has both plus and minus possible energies. So this was quite a strange at that time that the energy spectrum can be negative. But the good thing is that positrons were detected after 1 or 2 years, and that confirmed that the relativistic fermion can have both feature like positron and electron. So the positive energy refers to electron and negative energy refers to positive. So negative energy is for positron. So this was a very big triumph in physics. Then the scientists started tuning parameters of this Hamiltonian. So they tried to study a spin half but massless particle. So the thing is, they just set mass equals to 0 in the Dirac Hamiltonian, and once you set mass equals to 0 in Dirac Hamiltonian, then the Hamiltonian commutes with the helicity operator. So the helicity is the projection of electron spin. Here it is sigma with the momentum. So it can have two definite values for a massless particle, either +1 or -1. So let's say if this is the spin and this is the momentum, then this is the projection of its spin on the momentum. So this is what gives the helicity. So the Weyl Hamiltonian have a well-defined helicity. But the thing to keep in mind is after like 70 or 80 years, there are no fundamental massless spin half particle only exist in uh, spin half particle with zero mass only exist in pen and paper, but not in reality as a fundamental particle. So no spin half massless particle exist as a fundamental particle. Okay, so then the scientists started to look into band structure. So they come up that in crystal structure, electrons travel with Fermi velocity, which is equals to 10 raised to power 6 meter per second. It's quite it's a big velocity. So the thing is. In band structure, electron can have a linearized spectrum, and they can, if the spectrum is linearized, then it has zero curvature, because we know that the mass is so the mass is the curvature of so the mass tensor is the curvature of energy spectrum. So this can be so So this is possible that the mass of a spin-half particle becomes zero in band structure. So, uh, if energy bands are crossing each other, then they can have a linearized spectrum, and such bands can be described by two by two matrix. So this is the condition uh, for having a linearized energy spectrum in three-dimensional uh, spectrum. So one thing one should address is here is graphene. So graphene has two-dimensional is a two-dimensional material, and it has two-dimensional spectrum. So it does not fit in category of Weyl semi-metal that needs to be in three dimension. So this is but this is also possible that the energy spectrum can have a linearized spectrum in three dimension, and then one can speak of a massless relativistic spin half particle. So this is energy spectrum of a massless particle because it is linearized, and these are reference to the helicity. So one can see the momentum can be parallel to the spin or can be anti-parallel to the spin. So these two possibilities are there. While discussing three-dimensional Weyl fermions, it is very interesting to include or to discuss a Berry phase effect. So, if I recall that if we have a solenoid and we make electron beams to pass through this solenoid and interfere, because electrons behave as wave because they are very small, so they can interfere and form this kind of spectrum that shows interference pattern of dark and bright bands. So when we turn on or turn off magnetic field, or we tune magnetic field, then these interference bands moves by changing uh, magnetic field. So this effect is explained by the Berry phase effect. In general, in quantum mechanics, a wave function is not unique, so one can always define a phase factor uh, with the wave function of a particle. But the Berry phase is something that requires some condition, and the condition is if we are talking about a parameter in Hamiltonian, we are tuning a parameter of the Hamiltonian, then we need to be cautious that we are not spontaneously changing the Hamiltonian. We need to adiabatically tune this parameter around a closed loop to get to Berry phase. So if we are in a ground state and we are expanding it, the parameter, then the wave function should remain in the ground state, and then the adiabatic continuity is a very essential feature of Berry phase. So this is how the Berry phase is entering into physics, And one practical observation is in this experiment where we pass electron beams across solenoid and see the effect of Bary phase. The Dirac Hamiltonian has a spin, and spins have intrinsic Bary phase. Here one should here we need to connect the Bary phase or the Bary vector potential with the vector potential that we see in electrodynamics course. So the vector potential is not something that is observed in laboratories, but the curl of vector potential, that is magnetic field, that is observed in laboratory. So similarly, Bary phase and the Bary vector potential is not something that is observed quantity, but the Bary curvature, that is the curl of the Bary vector potential, is something that is observed in laboratory. So the curl of the Bary vector potential gives this field, which is varying with 1 by k square. We call this as effective magnetic monopoles fields. This is the monopoles field because we know that that if we have an electric charge Q, then at a distance r, then its electric field decreases with 1 by r square. So here the field is decreasing with k square. So that's why it is called the monopole field. And this is the effective magnetic monopole because there are no magnetic monopole observed as a fundamental particle yet. So these only exist in band structure of solids. So if we talk about the effective magnetic monopoles, then we want to detect it, then we need to break two symmetries if we want to detect effective magnetic monopoles in band theory. One is we can break time reversal symmetry, or we can break inversion symmetry. So if we are breaking time reversal symmetry, then what happens? Then these two cones are split in momentum space. But if we are breaking inversion symmetry, or we are introducing some spin orbit coupling, then we are splitting these cones in energy space. So without breaking inversion symmetry, if we probe the Fermi surface of these metals or semi-metals, then we see these closed loops. So this is the situation when we are protecting the symmetry. But when we break the symmetry, then we observe this kind of Fermi arcs. So this is the signature of Weyl semimetals that we will be observing Fermi surface. We'll be observing a Fermi arc in these semi-metals. So what is happening here, that we are in bulk, we are having energy spectrum that is dispersing linearly, but on the surface, these linearized energy spectrum will be making Fermi arcs. So this is some nice illustration of effective magnetic monopoles. So we have a source effective magnetic monopole and a sink effective magnetic monopole, and on the surface these forms Fermi arc. So the field starts from the source and terminate into sink. The thing is, these are in actual the band structures that will be formed in these semi-metals. And one thing that should be discussed here, that these Fermi arcs are not topologically protected. So if we study transport, then the impurities definitely can play a role, and one can see impurity effect as well. So these are not the topological features at all, but these are but there is a connection between bulk and surface, and that connection is the formation of Fermi arc in case of breaking of time reversal and inversion symmetry. And this is the detection of Weyl spectrum. So first time it is observed in tantalum arsenide by two experimental groups. These are the density functional theory data, and this is the experimental data, and they have did the photoelectric effect. So these arc are formed on the surface of tantalum arsenide. So they are sending vacuum ultraviolet radiation or light source to detect these Fermi arcs, and then to probe the deep band structure, they send soft X-rays of the order of point electron volt, and these are the density functional theory. Similarly, the second group have observed these Fermi arcs, and they have these linearly dispersing energy spectrum. So this is the crystal structure of tantalum arsenide, and this breaks inversion symmetry. So there is a spin-orbit coupling, and that's why there are Weyl fermions, and one can observe these Fermi arcs. Now we shall focus on magneto-transport study of these Weyl fermions, but we first and we will be taking help from the very conventional Drude theory, that is a very simplified model of studying transport in metals and semi-metals. So the first thing to start this study is this Lorentz force that we have seen in our school. So there is an electric field and there is a magnetic field, and then there is this Ohm's law that connects electric current with this electric field, and conductivity is the linear response. By solving this equation, one can extract these conductivity matrices, and this omega c is the cyclotron frequency that is equals to EB by m star, where m star is the effective mass. And one can see that the conductivity decreases quadratically with magnetic field. So these are about sigma xx and sigma yy, which and these are perpendicular direction with respect to the applied magnetic field. So we are considering magnetic field is applied along z-axis. So along the direction of magnetic field, there is no effect that is seen, because Lorentz force effect is only seen in direction that is perpendicular to applied electric and magnetic field, whereas there is also off diagonal conductivity, which increase linearly with the magnetic field if omega c tau is very small than 1. And then we speak about the resistivity or the magnetoresistivity, which remains constant, and these magnetoresistvities are independent of magnetic field, whereas the Hall resistivity increase linearly with the magnetic field. And this is the transport time of these metals. So this is the simplified theory. This does not include the Berry phase. Okay, now what we observe in cadmium arsenide. Cadmium arsenide is a Dirac semimetal. So this is the crystal structure of cadmium arsenide. And so this is here we see this sample, and we are seeing magnetic field making some angle with electric field, and when the electric field and magnetic field is in the same direction, so this is theta equals to 0, and the second graph shows the theta equals to 0 case, and we see that these resistivities decrease by increasing magnetic field. And in our previous slide we have already shown that from the Drude theory the resistivity should stay constant, but this is not the case here. So this is observed in Weyl semimetal. And we also see another thing, that when electric field and magnetic field are perpendicular to each other, then the resistivity along the direction of along electric field direction rho xx is linearly proportional to magnetic field. This is also something that is not consistent with the Drude theory. So this rho zz is or the Magnetoresistivity along the direction of magnetic field is decreasing with magnetic field. This is a new observation, and this is new observation that the magnetoresistivity in perpendicular direction of magnetic field increase linearly with magnetic field. So this is what is not consistent with the Drude theory. Now we will try. Now we will try to make it consistent with the Drude theory. But before that, we also discussed this half Hustler metal. This is also a Weyl semi-metal, and here we also see this decrease in resistivity, and this is symmetric, and this is decreasing with 1 by h square. And in this semi-metal, we also see the planar Hall effect. So the planar Hall effect is something that is observed in plane of electric and magnetic field. So if this is electric field and this is magnetic field, then there will be a signal that is formed in this plane. So this is the planar Hall effect. And if and this planar Hall effect is arising not because of the spin and charge coupling, because planar Hall effect can be observed in magnetic materials or scattering due to the magnetic impurities, but this planar Hall effect is not arising due to those impurities, but these are arising due to this anomalous observation in this Weyl semi-metal. And then we will also then we will also discuss the nickel ditelluride, which is type 2 Dirac semi-metal. And in this semi-metal, the experimentally, this is the negative magnetoresistance is not observed in nickel ditelluride, but this still shows the planar Hall effect. So we will discuss that a possible mechanism of this planar Hall effect in nickel ditelluride, which is type 2 Dirac semi-metal. And here this planar Hall effect cannot arise due to the chiral anomaly, because the Berry phase effect is not present here. So these decrease in resistivity are refers to the Berry phase or Berry curvature effect. And this is so this system is not showing the Berry curvature influence in magnetoresistivity. So we cannot say that the planar Hall effect is arising due to this Berry curvature effect. So these are things that are also inconsistent with the Drude theory. So what we have done, we have included Berry curvature in Drude model to understand negative magnetoresistance, and this is very well known in theory. To understand these negative magnetoresistance, one include the Berry curvature, and then these negative magnetoresistance can be explained. And the inclusion of Berry curvature also explains the planar Hall effect. So this has been already done in theory. But what we have done, so there is a force due to the Berry curvature, and the nature of this force is like this force is directly proportional to E dot B and then omega, where omega is Berry curvature. Whereas we also know that the Lorentz force is V cross B. So we try to compare the effect of these two forces, because one force is like E dot B and this force is V cross B or E cross B, because this velocity will be the drift velocity. Not the drift velocity, but the effect is observed in a direction that is perpendicular to electric and magnetic field. So we have compared these two forces, that is the Lorentz force and this Berry curvature force. So we will discuss this, and the second thing is we will discuss the planar Hall effect that can arise even if we do not include this Berry curvature force. This can arise by considering the violation of Lorentz symmetry. So violation of Lorentz symmetry means the energy spectrum is angle dependent, so it has different along different direction the spectrum is different. So then this can give rise to the planar Hall effect, which makes sense. So we shall also discuss this, and this give rise to planar Hall effect not only in the semi-classical theory but also in quantum theory. So we will discuss this as well. So this is Dirac Hamiltonian, this is the spectrum, and this is the eigenstates, and this is the Berry curvature calculated from these eigenstates. So by using the Wigner-Moyal approach to the Boltzmann equation, or one can use the Keldysh technique, or one can use the wave function, block wave packet wave function expansion technique to derive these equations. And in these equations, the important thing is these Berry curvature terms. So I usually discuss this force term because this is also important for us. So you can see that here it is proportional to the E dot B, which means the effect can be seen in plane of E dot B, and this gives rise to the planar Hall effect that one can observe in these Weyl semimetals. So for discussing this Weyl semimetal, we use a very simplified model that is the relaxation time approximation. So this means we have a Fermi surface and we apply a electric field, and this Fermi surface is pushed, but because of impurity, it is relaxed in transport time theta r, and that is this relaxation time. And then we have this well-known continuity equation that is satisfied for both particles, for both left-handed and right-handed particles. But the thing is, if we take the difference rather than sum of these particles, if we replace this with minus, then this continuity equation is not satisfied, and this leads to this population imbalance of the left-handed and the right-handed particle. And now we calculate the current along the direction of magnetic field, that is the z direction, and we see that the conductivity increases quadratically with the magnetic field, and this is consistent with the experimental observation. And one can also see the population imbalance increase linearly with the magnetic field. So one B dependence enters from here and one B dependence enters from here, and this gives rise to B square dependence in this conductivity that gives rise to the negative magneto-resistance in Weyl semimetals. And this is what we are doing here. We have electric field, we have magnetic field, and we are changing angle of electric field with respect to the magnetic field. And when the angle between electric and magnetic field is zero, then we are in a situation where we are considering the maximum Berry curvature force, because Berry curvature force is directly proportional to the E dot B. And when angle is zero, then this effect is maximum, and we see this increase in the conductivity. And when the angle is 90, then the Berry curvature force is absent, and then we see this decrease in resistivity that is quadratic. Now what can happen, that we can have a situation where this Berry curvature force and the Lorentz force can compete. So this we are talking about, let's say theta equals to pi by 6, and we see that here we are seeing a minima. So there is a decrease in this conductivity, and this decrease is due to the Lorentz force, and then there is an increase in the conductivity, and that increase in conductivity is due to this Berry curvature force. And then there is a competition between Lorentz force and the Berry curvature force. And when these forces are equal, then one can see a minimum in the conductivity. So this minimum can also be tuned by the purity of the sample, or by mobility. So this minimum can be pushed or can be tuned by the mobility of the sample. So this is one thing that I wanted to discuss. But experimentally, we have seen the magneto-resistance plot, and in magneto-resistance, we see that the resistivity decreases quadratically when the angle between electric and magnetic field is zero, whereas when angle is 90 degree, then it is constant. And this is consistent with the Drude model. So there is no Berry phase effect when, because in E dot B, when angle is 90 degree, then this is equals to zero when theta is 90 degree. So no Berry curvature effect can enter here. So this is almost constant. But experimentally, we see that when angle is 90 degree, then the resistivity increases linearly with magnetic field. So to be consistent with experiment, we add a phenomenologically magnetic field dependence in transport time, and we fit this with the experimental data. But there is a lot of controversies in theories. Those are present for this B dependence in topological materials and these Dirac and Weyl semimetals. So there is no one theory that can explain this linear magnetic field dependence. So our concern is this negative magnetoresistance. And the thing is, if a material shows this if the material shows this linear increase in magnetoresistance, then one cannot compare the Lorentz force and the Berry curvature force. So this can be only seen if this is not present. So we don't want this if we want to compare Lorentz force with the Berry curvature force. So this is not something that is good. Okay, so this was experimental data that we have successfully fit in with the Drude model by including a Berry curvature force by including a Berry curvature force that is directly proportional to Berry curvature and E dot B term, and by including a phenomenological time dependence in transport time that is 1 by b, then we have fit this experimental data. So this is how we have fit this data by and try to explain these results by a very simplified Drude model. Now we will focus on the planar Hall effect. So like I have said that the Berry curvature force is directly proportional to the E dot B term, which is directly proportional to the Berry curvature. And because of this term, we have this negative magnetoresistance. And this can also explain planar Hall effect. So Hofstadter is a Weyl semimetal and it shows both of these effects, and these are arising due to this Berry curvature. But nickel ditellurite is type 2 Dirac semimetal. It does not show this Berry curvature effect. We are not seeing the negative magneto-resistance, but we are seeing the planar Hall effect. So this planar Hall effect can be defined by considering considering the violation of Lorentz symmetry in these semi-metals, because the spectrum is angle dependent, and because of this angle dependence, this planar Hall effect can arise. Now we will discuss this. So this is the Hamiltonian of Dirac semi-metal. But we are introducing this term that makes the spectrum angle dependent. When we have this term, then the spectrum becomes angle dependent. But now we have two competing parameters. One is Vf and V tau, that is the tilt velocity. So if V tau is smaller than Vf, we have a closed Fermi surface. If V tau is greater than Vf, then we have a parabolic Fermi surface. So the thing is, if you are applying a magnetic field that is strong that is so strong that can quantize charged particle, but if we are trying to applying magnetic field then the magnetic field cannot quantize these intrinsically open orbits. So this thing one need to be careful. So there are no solutions that are possible for open orbits to become closed when there is this type of open orbits or type 2 semi-metal. So this is the type 2 structure and this is the type 1 structure. In type 2 structure, we will have open Fermi surface or open energy contour, and in this case we will have this type of closed energy contour. In this case we will be having like this type of energy contours, so that will be like parabolic. So these are like parameters one can see: type 1 elliptical, type 2 hyperbola, and type 1 circle. Now this is the quantum study of magneto-transport through Dirac and Weyl semimetals. So here we have replaced these momentas, because these momentas now include the magnetic field. Because magnetic field is applied along z direction, so Pz will remain unchanged. But we see that now this Hamiltonian has become very difficult to diagonalize, because every elements of this matrix have magnetic field dependent momenta. So but one can solve this by hyperbolic transformation, and this has been done, and one can diagonalize and find this energy spectrum. So this is the energy spectrum of type 1 Hamiltonian, and this is the energy spectrum of type 2 Hamiltonian. This is the ground state which disperse linearly, and this is the first excited state, and this is the ground state for type 2, and this is the first excited state. And now we discuss tantalum phosphide. So we have this. This is the energy density of this Dirac or Weyl semimetal, which is parabolically increasing with energy. And when we apply magnetic field, then there will be these Landau quantization effects. So one can see these Landau quantization effect, and one can also see that these spacing are uneven because Landau quantization in a linearized spectrum goes with the square root of b. If this is 2D or 3D, then these will be even because their Landau quantization goes with b. But here it is a square root of b, so that's why this will be not even. This will be uneven. Right, this is the thing. And about tantalum phosphide, as these are the experimental data. So this is the quantum lifetime, and this is the transport time. They are of the same order. So this suggests that we don't need to do extra order calculations of impurity. So we are good with the first order term, and this is the Fermi energy, that is of the milli electron volt order, and this is the impurity broadening, and this is the mobility of the sample, that is quite good for not considering higher order terms. And now we have this current correlation function, or this is for calculating these Hall magnetoresistivity and the longitudinal magnetoresistivity that is perpendicular to applied magnetic field. We see these plateaus. So there are these plateaus. These are also seen in 2 dimension, but in 2 dimension they are very pronounced because and the reason is in 3 dimension we have a third direction where electron can escape, and in actual we are integrating here along the third direction, and because of this integration we have a background, or the pronounced feature is dyed. And same happens with this longitudinal magnetoresistance. And there is another difference between the conventional 3D magnetotransport along the longitudinal direction and or along the direction of magnetic field, and in this Dirac or Weyl semimetal, that is these plateaus are formed along the direction of the magnetic field. These are not observed in conventional 3D materials, and the reason is there can be a scattering so this green function can be of particle and this green function can be of hole. So because of that reason, these plateaus can arise in the longitudinal in magnetoresistance along the direction of magnetic field. Finally, we discussed the planar Hall effect that can arise in the press because of this tilt velocity. So the tilt velocity in plane of electric and magnetic field, and because of this there is a developed voltage. So this is the Hall voltage, and one can see that the Hall voltage can give rise to this semi-metal, even though there is no Berry curvature effect, and this is directly proportional to rho ZZ, which oscillates. So there is also this kind of oscillation possible in the planar Hall effect. So this is something that suggests that in type 2 Dirac semi-metal, one can observe planar Hall effect without the need of Berry curvature effect, even if the Berry curvature effect is absent. Now, because the spectrum has the angle dependence, so when one do the calculation, then the integration around the closed loop is not zero along this direction of x and z, and this gives rise to this planar Hall effect. So this can also be referred to as the mobility is different in different direction, or the spectrum is different in different directions. So that can give rise to the planar Hall effect. And this is the conclusion. So we have discussed the negative magnetoresistance in Dirac and Weyl semimetals, and this can be explained by the Chiral anomaly or Berry curvature effect. And longitudinal magnetoresistance shows Cherenkov-de-Haas oscillation. This means rho ZZ, which does not show Cherenkov-de-Haas oscillation in conventional 3D materials, but it does shows Cherenkov-de-Haas oscillation in three-dimensional Dirac and Weyl semimetal. And we can also explain planar Hall effect in Dirac and Weyl semimetal if there is a Berry curvature effect present. But we can also explain planar Hall effect in Dirac and Weyl semimetal even if the Berry curvature effect is not present, but the Lorentz symmetry is not present. So these are the conclusions. Thanks for listening these lectures that introduce Dirac and Weyl physics. And these are the references that I have used in